Welcome to my YouTube channel. This is the third lecture on the lecture series based on Einstein's general theory of relativity. In Newtonian mechanics, the idea of space and time is completely different. In Newton's first law, a free particle moves on a straight line at constant speed. So, in Newton's first law, any free particle moves on a straight line with a constant speed. But how we define a geometry of a straight line and how we define time? Time t and x, y, z. How we define geometry of this straight line? The straight line of Newton's first law is shortest distance between two points. So, a straight line in the Newton's first law is the shortest distance between any two points A, B, and the line element of this is dx square is dx square plus dy square plus dz square, and this is based on 3D Euclidean geometry. Now you can see that this line element actually defines flat space. So this is the line element of the flat space. The line element of flat space, and any coordinate system or any reference point which is moving with constant velocity v constant is defined as inertial frame, and in the inertial frame this is the line element. So a car moving with constant velocity is defined as inertial frame, and Newton's law holds only in the inertial frame, or we can say that any frame in which Newton's law hold is also called inertial frame. Now what is the connection between two inertial frame? Suppose this is frame 1, this is frame 2. The coordinate of frame 2 is x dash, frame 1 is x, y dash, y, and the distance between the origin of these two frames is d. Then what is the connection of the coordinates between these two frames? Then we can say that x dash is equal to x minus d. Same way y dash is equal to y, z dash is equal to z. This is the relationship between the x coordinate of frame 2 and x coordinate of frame 1. If we differentiate these three equations, what we will get? Now d is also can be written as vt. V is the velocity of the frame 2 with respect to frame 1. So x dash is equal to x minus vt and y dash is equal to y, z dash is equal to z. This is the relationship between two inertial frame of a reference. Now if we differentiate these three with respect to t, then we will get dx dash by dt is equal to dx by dt minus v, or v dash is equal to vx dash is equal to minus v, or vy dash is equal to vy, vz dash is equal to vz. So this is the relationship between the velocity of any particle p from the reference point f2 and reference frame f1. Suppose instead of two reference frame in straight line, what we do, we rotate frame 2 with respect to frame 1. This is frame 1 and we are rotating frame 2. This is f2. Rotation angle is phi or theta, we can say phi. So this is x dash, y dash. Now we can say what is the connection between frame f1 and f2 when the f2 is rotating at angle phi from f1. So the relationship will be x dash is equal to x cos phi plus y sin phi. Similarly, y dash is equal to minus x sin phi plus y cos phi, and z dash is equal to z. So this is the relationship between two reference frame when one reference frame is in rotation with respect to the frame 1. And here x is equal to x minus vt, y is equal to y dash, z is equal to z dash, and we know that in Newtonian mechanics time is universal. So the measure of time from one reference frame to another reference frame doesn't change, so it is same. So t dash is equal to t. So measure of time from the reference frame f2 is identical to time in f1. So these four equations 1, 2, 3, 4 are called Galilean transformation, which applies to inertial frame of reference, any two inertial frame of reference. So x dash is equal to x minus vt, y dash is equal to y, z dash is equal to z, and t dash is equal to t. This is called Galilean transformation, and it applies only in case of inertial frame of reference. So this is the definition of inertial frame.